also interested in just having things know the intent.
Are we rolling?
Are you assuming a soda? Wait.
Welcome. Yeah, I'm assuming soda.
Miss-
All right,
Miss
people
Jameson
are going to be
gave us-
trickling in.
Everyone's assuming.
Let me know also, John, if this is burdensomely tough to
No, I'm okay.
and be present. Good. Okay.
Or put it
And you can't hear.
Here's the fly.
Oh.
Awesome.
Yes. You like that?
Oh, I know why you're happy.
You like the flowers?
Why? I know why you're happy.
You're excited for the webassign that's due the next time we meet? Absolutely. It's going to be a good webassign. We're going to talk today about electrical potential energy and voltage, topics that you were already introduced to in those worksheets. But today we will codify what we know. Okay? Let's talk generally about potential energy. And if I say that this height is y defined as 0, would you say that the gravitational potential energy of this system, the ball in that configuration, is positive, negative, or 0? Joseph. Oh, I'm sorry, I thought you were raising something. No. Potential energy, positive, negative, or 0?
Positive.
Positive. How do you know?
Do that. Above the line, 0.
Great, because y is positive, the potential energy on Earth is mgy. Great. In this configuration?
0.
In that configuration? Negative. Great. Energy is a scalar, even though there is some preferred direction of motion when we talk about systems and their configurations and their reconfigurations. Energy is not a thing that has a direction. It can be positive or negative. The place where we choose to call y equals 0 is an arbitrary choice, and it has no physical significance. When I say it has no physical significance, what I mean is that anything that matters, people are going to agree. The amount of work that's been done matters. How much kinetic energy? If you don't mind, we just scoot over just a little bit because I'd like John to be able to film us, and it's flattering. The reason is that say hi to period 2.
Hi, period 2. Let's watching on. Snow day. You will have a first when you come back.
Okay. The 0 of potential energy is arbitrary. Any question that I could ask that is worthwhile, different observers would agree on. Whether or not a person defined y equals 0 down here or at the top of the house, people would agree on the question, how much kinetic energy does the ball have? People would agree on the question, how much work did the gravitational force do on the ball when it moved from that position to that position? That's what I mean when I say the 0 potential energy is arbitrary. Okay? In the absence of external forces, systems tend to reconfigure themselves in the direction of higher potential energy or lower potential energy? Lower potential energy. Sometimes that involves moving from 0 to a negative amount. Sometimes it involves moving from a negative amount to a more negative amount. Is it always the case that every system always goes towards less potential energy? Well, kind of. I can make the apple, though, rise in potential energy.
But it's not falling towards higher.
You're like exerting an external force.
Yeah, I would say a key idea here is that I am coming into the Apple Earth system and exerting I'm exerting an external force. An external force is doing work that accounts for this increase in gravitational potential energy. Okay, what am I doing here? I'm reviewing some key concepts from the energy unit that are going to be important when we start talking about electrical potential energy and voltage. The work done by an internal force is minus the change in potential energy. Remember that from our energy unit? That is just saying in math this statement. The internal force of gravity, internal to the system of the apple and the Earth, did positive work because, how do I know that the gravitational force did positive work when the apple fell?
Just direction.
Because the force was exerted in the same direction as the displacement, and when that occurs, the work done by the force is positive. A positive amount of work resulted in a lowering of potential energy. When the system was left to do what it wanted, it exerted a force that was, of course, in the direction of the motion that the force created. did positive work, resulting in less potential energy. This sentence in English is that sentence in math. Raising the potential energy of something takes external work. One example of lowering potential energy is going from 0 joules to -5 joules. The fact that we call a potential energy negative has no physical significance. It sounds like I'm just hammering that into the ground in this example, but when I talk about universal gravitation potential energy function, you'll be like, oh, and you'll remember. I said, oh yeah, the fact that the energy is negative doesn't mean anything. It's just a question of whether energies are getting larger or smaller. We already said this, again, I'm talking about important things from the energy unit. When the force points along a displacement, the force does positive work. When the force points anti-parallel to a displacement, it does negative work. That came from our dot product understanding, right? The work was related to the dot product of forces and displacements. If the angle between them is between 90 and 180 degrees, then the value of that cosine is negative. Negative work is done. All right. This is the greatest hits of our energy folder. When I do this, and the worksheet 1 asked you about this too, I'm lifting the barbell. I do positive work or negative work? Positive. And does gravity do positive work or negative work?
Negative.
Negative because it points that direction during an upward displacement. Downward force, upward displacement, negative work. If I raise it from rest to rest, what is the net work done on the apple?
Change in potential gravitational energy.
No, so not the change in the potential energy. The net work is the change in the kinetic energy of the object. And if I raise it from rest to rest, it started with 0 and ended with 0 kinetic energy. The positive work I did canceled the negative work by gravity, yielding 0 net work, yielding no change in kinetic energy. All right. That's all review. This is a little bit new. I propose to take a positive charge and another positive charge and make them be really, really, really far from each other. Let's say you get to make the rules. Would you like to call the amount of potential energy in this setup positive, negative, or 0? And you know that you already have a formula that yields the answer. But if you had your druthers, just qualitatively, if I hadn't told you the formula for potential energy, would you like to call this 0 potential energy, positive potential energy, or negative potential energy? Joseph?
0.
You like 0?
Because we did the same thing in gravity. So
We definitely did. Is true. Did you want positive side? How come?
It seems to be not any great distance.
I guess there is something very positive about this situation. The charges are positive. The distance between them is positive.
That's
I feel it.
formula, of course.
I feel it. Yeah. Anyone want this to be negative potential energy? When we, it doesn't mean anything. I agree. I'm sorry?
Why deal with the negative if it doesn't mean anything?
That's a really good point. I like it. Remember when we did gravity and I brought one object there and one object over there? I sort of said something that was like, well, maybe this is an okay place to call 0 potential energy because, remember, this was a small point and, as Amina correctly points out, not important.
Which place did you call 0?
Infinitely far separation. Yeah, they're not really interacting with each other. I feel comfortable calling that 0. When there's no interaction anymore, when they're infinitely far, let's call that the 0 potential energy. Now, this does matter. If that is 0 potential energy, is this going to be positive potential energy or negative potential energy? Take a second, take 30 seconds and talk to your neighbor.
I'm going to say it's negative because the displacement is pushing the positive.
Big R is
Yeah, but to actually like where they want is
about we're not. We're not. I want to move towards what we do, so they're
all right.
be far apart.
If this is 0, we're constrained to accept this is the 0 of electrical potential energy. Should this be positive potential energy or negative potential energy? Shivani, what do you think?
I think it would be positive because I don't know, just like thinking about in like the topics when we said that it's considered positive to like get them, or I don't know, like when I think about like math or like gravity and masses, like when you raise the potential energy, it's like harder, and like I guess since you're like trying to squeeze them together, it would be harder.
Yeah, I find that very convincing. That raising the potential energy of the system takes external work. Lowering the potential energy of the system, all I have to do is take my hands off. When we move from this configuration to this configuration, is external work required, or do I just take my hands off and that happens? External work is required. So does going from there to there represent an increase in potential energy or a decrease? An increase. If we had just started at 0 potential energy and increased the potential energy, this is a picture of positive potential energy. Bringing these charges together is like raising the thing that doesn't want to be raised. 0 potential energy, positive potential energy. What am I about to do now? I sure am. Infinite separation. Let's call this 0 potential energy if you don't mind, because they're not interacting, they're far. Infinite separation. Sad?
What if you put the charges on top of each other? Isn't that 0?
That would be, in addition to maybe being difficult to achieve, as you know from the formula, it's going to result in like an infinity of potential energy.
So we've done it.
Yeah. All you have to do is cause 2 opposite charges, preferably a large charge, to occupy the same space, and we'll shut down school for the day. Period 2 will still have to watch. Okay, I've got a big positive charge, I've got a positive charge and a negative charge, infinitely separated. 0 potential energy. Is that picture, where they have a small finite separation, is that a picture of positive potential energy or negative potential energy? Jack?
I'd say negative.
How come?
I'd say because if you let them go, they want to move towards lower potential energy and they move closer together.
Okay, I can just release them, take my hands off, and they are going to attract each other. They will naturally accelerate towards each other to this position. When a system reconfigures itself in the way that it naturally wants to, it tends to lower its potential energy. If we start with 0 potential energy and lower it, we have gotten to negative potential energy. So this kind of thinking is going to be important to not just potential energy, but voltage. And I'm always thinking by analogy to raising or lowering my apple, and whether I'm doing external work, whether it's hard, whether it's easy, whether I can just take my hands off and the system naturally moves to this picture from potential energy equals 0, so there's negative potential energy there. Great. I asked if you would prove this as the last part of the first worksheet. It involves integrating the Coulomb force with the limits of integration from infinity to R. I don't think I'm going to show you that proof. But there it is. How is this different from Coulomb's law?
R isn't squared.
That's right. I noted in the voltage worksheet that if you wanted to make me cry, confusing electrical potential with electrical potential energy is a good way to do that. But even before we get there, if you want to make me cry, put an R squared in that formula. Or write Coulomb's law and forget the R squared. I really effective.
If you want to get a better way.
This is a scalar. It doesn't have a direction. It could be positive, negative, or zero. A key difference here is that I'm actually asking you to substitute the amount of charge, including a negative sign, if it's a negative charge. If there's one positive charge and one negative charge, is the potential energy positive, negative, or zero? Negative. Negative. Does that ring a bell?
Mm-hmm.
When?
Last slide.
Just now. Last slide. We just said it should make sense. A positive and a negative charge would have a negative amount of potential energy. If there were a negative and a negative charge, positive potential energy, negative potential energy, or zero? Why?
Because it takes force to
Keep them together.
Yes, if I start with two negative charges at zero potential energy, at infinite separation, I force them in, they're fighting, they're repelling, the negative and the negative are repelling, so I, as an external force, have to do work to get them to finite separation. So yeah, a negative and a negative should have a positive potential energy, and they do. The electrical potential energy in the system is the amount of external work required to bring the charges from an infinite distance to a finite distance. Okay. If the amount is negative, then the system releases energy by moving there. This is releasing energy. Sort of converting that potential energy into kinetic energy. So, all right, what do we got here? Example is, let's say I've got a 3 microcoulomb charge fixed in place and a 5 microcoulomb charge that has a certain mass that's initially a certain distance away. What is the final velocity of the object, of the second charge, once it's repelled and it's very far away? Here you go. They're both positive charges. They start at a finite distance. What genre of problem is this? Conservation of mechanical energy. Only internal conservative forces act. So mechanical energy is conserved. The electric force is a conservative force. We know that because it has a potential energy associated with it. Only conservative forces have potential energies associated with it. So how do we do it? What would we write? Anyone I haven't heard from? Sonic's right.
Well, you could calculate the potential energy in scenario 1, and then you know in the really far away, the potential energy is 0, so it has completely switched to kinetic energy, and then you can solve for loss.
Great, that's right. Potential energy converts entirely to kinetic energy, set them equal, solve for the unknown. So?
Is there a way to figure out
If Q1 wasn't fixed, like, and they both kind of went apart from each other?
It sounds like that is a situation where both momentum and energy would be conserved. And so you'd have two unknowns, that is to say the final velocity of both of them, but maybe you would have a conservation of momentum and a conservation of energy equation. So I say yes. The total momentum being 0. Cool. I'm not interested in the solution to that. I'm interested in you understanding that this is a conservation of energy problem. It's the electrical potential energy between this walrus of positive 1 coulomb charge that's 2 meters separated from this triangle with the walrus inside of it with the total charge of -1 coulomb.
Do you have to integrate because they're not from charges?
Thank you. This is an expression for point. This is an expression for point charges. These are not point charges, nor should they be treated as point charges because they are close to each other compared with their spatial extent. So we if they were super far away, maybe this would kind of be like a point charge, and that would be kind of like a point charge. So yeah, we don't have enough information to answer this question.
Not the R either. Like that 2 meters is completely.
Yeah, R is what to what? The center of charge distances. We don't really have a way to answer that question. We're not gonna do it. We will do integrals. We just won't do that. That's what your level is. My interest here is also not that you solve the question, just that we talk about the first step. How can we find the total electrical potential energy in this system? Vanessa?
I think you do the potential energy between two and add it to
You're
add them all together.
There are 3 pairs of charges. These two, and those two. And there's potential energy between each of those pairs. So yeah, that's right. Why is this true? Well, one thing is you could imagine that there's just the +5 microcoulomb charge, and you could be like, how much work do I have to do, or how much work is released when I take this second charge from super far away and put it there? The amount of work that was released from the amount of external work I had to do to bring that charge there represents the amount of electrical potential energy. Now, those two, so by the way, the electrical potential energy between those two is the amount of work that I had to do to bring this blue in, and the amount of energy that was released as it was brought in. Then I imagine bringing this one into infinity, from infinity, and as I did that, this new charge interacted with that charge and that charge. So there was potential energy from the interaction of these two as I brought that one in. Then as I bring this one in from infinity, there's the interaction that it has with the +5 microcoulomb and the interaction it has with the -3 microcoulomb. So what's up with this? Why am I using microcoulombs? Yeah, why not just coulombs? Anyone know? Because it's huge. Really big. I was actually just talking to Dr. Morse, and he was saying that one of the things that he's advocating in particular for questions on APs is that they have reasonable sizes. I actually saw there was a physics teacher that I talked with who's in the first year right now, and I asked if I could see one of their tests, and they showed me a test, and it was really nicely done. It did involve a collision between 2 bowling balls. This was when they were studying impulse, and the collision lasted 4 seconds. and so I ordered some of those bowling balls so that we could have them in the physics lab. Yeah, microcoulombs. Yeah.
When I first saw this, my instinct was to find the center point of the triangle and then treat it as a trio. I forgot geometry, so I don't actually know how to do that, but would that work?
I guess, like, is there anything that we could say about the center of charge? I'm not sure, because that's kind of what you're doing.
And we were saying, is it from the center of charge between the 2 objects? But then how do you?
Yeah, like I wonder.
In terms of the radius, because we were given the side length with the triangle, but I was like, oh, but if I find like a common radius, I give up on it.
I'm not sure what that produces. The one difference between center of mass and this is that when you talk about the gravitational force on Earth, force scales linearly with mass, which makes things mathematically nice in a way that maybe wouldn't work for this, because here forces scale quadratically or inverse quadratically with distances, and so a center of charge might not have as much that's useful as a center of mass does. Okay, we've done electrical potential energy. On to voltage, which is the same word as potential, which is the same word as electrical potential, which is very, very different from electrical potential energy. Yep. Yes. Thank you.
The moment you add energy to it, it's what I hate to write.
Voltage is the same as potential. They are both abbreviated with V, the letter V. It looks like a V. What are the units of potential? Joules per coulomb. AKA, there's one word. Volts. Oh, true. The volts is abbreviated V. So as I said in that worksheet, I could say, if I wanted to express the idea that the potential at a location is 2 volts, I would say the potential is 2 volts. The V's don't cancel, they stand for different things.
1 equals 2.
Potential energy. Potential energy is abbreviated, what symbol do we use for potential energy? U. And if we're talking about electrical potential energy, there's an E there. The units of potential energy are joules. Great. Probably should have done that after I explained what potential is. But again, a very effective way to make me cry is to read a question that asks you what the potential is and write some things in your test that makes me see that you were misinterpreting it as potential energy.
So is one capital and one lower?
No, I'm sorry, they're all capitals. Yep. That's right. If you want, you could think of this as, this sign, a caret, like if you're typing, like 6 to the 2 is 36. If you want, you could think of this V as an upside down subscript caret. Oh my God. I don't recommend it. No, don't worry about it. Missed it. Yeah. Okay. Yeah. We're going to talk about potential in the same way that we talked about electric field. If you remember, with electric field, we first defined it in terms of its effects. I said there's some distribution of charges that creates an electric field here of 5 newtons per coulomb in that direction. Now answer some questions about that. Only later did we actually write down that the electric field from a point charge was kq over r squared. We're going to do the same with voltage. Your knowledge, I guess, from the worksheet is what you'll use for this. When I take this 2 microcoulomb charge and boom, put it at 6 volts. If I brought it in from infinity, how much work did I just do? What, Sadik? 12. What was my question? How much work did I do? So you have to answer in joules. How much work did I do bringing this 2 microcoulomb charge in from infinity to a location that has a voltage of 6 volts? 12 times 10 to the negative 6. Let's say 12 microjoules. Cool. I'm going to start with it far away. And I bring this location. I'm not telling you what makes the voltage at that location be 0 volts yet. In fact, I'm not even sure there's really a distribution of charges that could create something like this, but if I bring this 2 microcoulomb charge in from infinity to a voltage of 0 volts, how much electrical potential energy in this system? 0. And if I instead put it there, -6 microjoules. Which is hard? Is it hard for me to bring it to 6, or is it hard for me to bring it to -3? 6. That's right, because starting with 0 potential energy, it's hard for me to raise the potential energy of the system from 0 joules to 12 microjoules. Energy is released as I allow this charge to go to -3 volts, just like energy is released when I allow the height of the apple to decrease. What am I about to do now? Negative charge. How much work is released when I bring that -5 microcoulomb to 6 volts? Minus 30 microjoules, and here 15 micro. Which one was hard? Bringing it to the 6 or bringing it to the -3? -3. So that's why? Because this is a negative charge, and this negative charge repels that negative charge? No. I have not told you that there's a charge there. This is a location. Voltage, potential, is a property of a location. Just like the electric field is a property of a location. I'm not saying there are charges there. In fact, there probably aren't if I'm proposing to bring a charge to that location. Okay. I believe that you all used this equation to answer that question up above. The potential energy associated with a charge being at a location. Man, that's a lot of words. I wonder why he chose to use so many words. Because
we did this exactly when we did. We had this. It's the. But I forgot what. Yeah. Anyway, we use the same words.
Yeah. Yeah, it's sort of hard. Yeah, with the electric field, we used a lot of words. It's defined in the conditional tense, sort of. It's defined by what would occur or what would be required or what the situation would be if a victim were brought to that location. This equation provides the definition of the electric potential, V, the voltage at a location. It's kind of fun. You've heard the word volts and voltage all your lives. This is what it is. It has to do with energy. It has to do with a particular location and how much potential energy would there be associated with a new victim charge being brought to that location. AKA, how much work would have to be done or released to bring a charge from infinity to that location. Electric field and voltage are both a property of a location. Electric field is a vector. V is a scalar. And I asked on the worksheet why that is or how you know that that's the case. It doesn't have a direction. Just the same way that energy doesn't have a direction. You might associate directionality about a scenario with differences in energy with different configurations. Too many words. But that doesn't mean that potential energy is a vector, nor is voltage. Electric field helps us calculate the electric force there would be on a test charge at that location. Voltage helps calculate the electrical potential energy associated with a test charge being in a particular location. And I consider field the force per unit charge at a location, and voltage is the energy per unit charge there. What are the units of potential again? The unit of voltage is volts. The unit of potential is volts. I don't have any, I know I've been playing some mean tricks on you with letters this whole year, with work being the same letter as watts, and power is work over time. So that gets confusing, but I can't get any more confusing than that. There's certainly nothing worse that I have up my sleeve after I tell you that V equals 2V.
I still believe that.
Yeah.
Just a question about the difference between E and V. So it seems to me like E is a continuous thing. So like you have like the electric field and it continually changes like all the time, whereas V is more discrete. Is that right?
Or like just V,
continuous
like-
versus non-continuous, I might say something along the lines of, remember we said the electric field was a vector field, that every location in space had that vector field associated with it, and maybe that's what you mean when you say continuous, that every location has one associated with it. We're going to find out that V is a scalar field, that when you have a distribution of charges, it causes each location in space to have a voltage associated with it. So it is continuous in that way. It's not just like this location has a voltage and then some ways away this location has a voltage. It is a continuous function of position. It's a scalar field. Zach?
What does like V measure the potential of, or electric potential?
Say that again?
What does the electric potential measure the potential of?
Ah, good question. And I think if I understand right, I'll repeat something I said when we studied potential energy for the first time, which is the idea of the potential for something to happen is not a good one to talk about, because I guess if we say, oh, the apple, and this is what they teach, 4th or 5th or 6th graders, the apple has the potential to fall, to get moving when it's on the table, so we say that it has potential energy. To which I respond, well, does that mean when it's on the floor, it has zero potential energy because it doesn't have the potential to fall? It does have potential energy. And what does it mean to have negative potential energy? I think that in the same way that those expose the fact that potential is not a great word to be using, that is not a great concept to put onto electrical potential either.
So there's basically a way to explain whether the charges move away from each other or
Maybe, but you don't have to have the potential of that happening in order to have a potential at a location. In fact, you don't even need a second charge. I'm going to do this in a few slides, just have a charge and say, what's the potential at that location? And it's not that we're saying something could happen, it's just a property of a location. I think it speaks for itself.
I don't think it speaks for itself. That is what? Babies can't talk. That is just
How much work
oh no.
to bring? How much work to bring the 2 microcoulomb charge from 0 to 6?
Well,
12 microjoules. How much? Ask me the question that, let's see, 18 microjoules is the amount of work
to move the charge released.
it's also released. It's not hard for me to do this. I don't have to fight it. In fact, if I just take my hand off, it will tend to happen naturally, just like if I release the apple, it tends to fall to lower voltage. So yeah, the question is, how much energy is released when I cause this charge to go from 6 volts to minus 3 volts? The amount of energy released is 18 microjoules. I won't do it with the negative charge. Here's what well, the fact that you do that indicates I did a bad job writing this line. All I'm trying to say is that the work is Q delta V. And maybe it's going to be positive and maybe it's going to be negative. We're talking about the work done by the electric field versus the work done by an external force. Just think about the question of, is the work positive or negative? Is the question, is the displacement along the direction of the force? The amount of voltage difference between locations times the amount of charge is the amount of work that a particular force does when a charge moves from one location to another. Many textbooks actually start with this. We talk about the amount of work to go from here to there, rather than talking about the potential energy of a charge being there versus a charge being there. And I think those textbooks are pretty smart, actually, because they avoid a confusion that I am going to have to unmake in a few slides. But I promise, this is, I think that you'll be happier. You probably haven't realized this confusion yet, so I'm going to introduce it and then eliminate it in the same slide, and you'll be happy, and I think you'll get it. Yeah. What did we just say? We just said, what was the left side of this equation? U, the electrical potential energy associated with a charge being at a location, is the charge times the voltage at that location. Here, I'm not taking a snapshot and asking what's the electrical potential energy. I'm taking a video and saying what was the change in electrical potential energy, what was the amount of work done. Does that answer your question? Is external work required? Positive charge naturally moves towards lower voltage. Someone make an analogous statement about the apple? What's like charge in the world of the apple? Then mass. Positive mass naturally moves towards lower height. Positive charge naturally moves towards lower voltage. Negative mass would naturally move towards, I wish I could do it, greater height. No, the acceleration is still
mass relative to air, so like a helium balloon has, or density, has a lower density than air. So
I kind of like that. I agree. Yeah, I guess the logarithm of the ratio of the density to the density of air. If it's negative, yeah, just simple, easy. Read on that. If I didn't, I just explained it would have avoided a natural confusion. Okay. Anyone able to tell me? This is a given charge Q. I haven't told you whether it's positive or negative, but I don't have to. And that's a distance R. This is a location. There isn't a charge at this location. What is the electrical potential at that location? It is V. Can you hit me in terms of the givens Q and R? Anyone I haven't heard from in a while? Roy?
K times Q squared over R squared.
K times Q squared over R squared. How did you get that?
UG equals Q is the, and UG is A times Q over R. Wait.
Let's see. What did we say the electrical potential energy of 2-point charges was?
K.
K. R squared. No, that makes me cry. No, it's not squared. That makes me cry. Good. R. By the way, what happens when I multiply a force times a distance? I get something that has units of what?
Newton meters.
Which is a? Joule. Sort of, yeah. I've been fast and loose about whether I'm dealing with a force or a distance. It's something measured in joules. This is the Coulomb force. This is an amount of force. What happens when I multiply it times a distance? I get something with units of... This thing has units of joules. See how that thing has units of joules? Because it's a force times a distance? Oh wait, I actually did want that. Boo. Yeah. K, Q1, Q2 over R. So is the answer, if I'm asking what is the electrical potential there, what's the voltage there, is the answer K times Q squared divided by R? No? If it were, what units would it have? What are the units of K Q squared over R? Joules. So it can't be a voltage. You divide that by a joule. We'll have to divide it by a charge. What would you like to suggest is the electrical potential at that location? is definitely B. KQ over R, let's find out. That is the result. Here's the derivation. Let's say I put a test charge there. Let's say I put a test charge there. Right? If I brought a test charge to that location, that is the amount of electrical potential energy that be, right? How have I gone from that line to that line? Associative property. That is the associative property of multiplication. That's right. I just pulled that out, and why did I do that? It's so that I can make a comparison to this line. What is that line? That is, someone I haven't heard from in a while. What is this line on the right side of our geometry proof?
Definition of potential energy.
That is the definition of electrical potential. It's the definition of this term. It's not really the definition of this term. It's the definition of this term, the electrical potential. So look. The electrical potential energy is equal to the test charge times the red box. The electrical potential energy is equal to the test charge times the red box. The red box must be the same in both cases. We proved that the electrical potential at that point is KQ over R. This is the voltage at a distance R from a point charge, and it is true whether or not that point charge is positive. That is to say, if this charge is negative, is the electrical potential there positive or negative? Depends on the victim charge? It can't depend on the victim charge because the voltage is the same whether or not there's a victim charge. Right, and if Q is negative, the potential at that location is positive or negative? Negative. What does that mean again? Nothing. It means that if I let a positive charge, right? This is good. This is important. If I say the voltage there is negative, what am I saying? I'm saying that a positive test charge would release energy if it's brought to that point. And that makes sense. It means because, right, forget that point. That charge, if it's negative, and I drop a positive charge about some distance away, energy will be released as it naturally comes to a distance that's closer to the negative charge. That's why the voltage is negative there. Because the potential energy associated with a positive test charge would be negative. It's a lot of words. Is the voltage at that location? It's not a fusion yet.
99 2 coulombs of R1.
What do you say? Oh, 9E9. Good call. Okay, 9 times 10 to the 9. Maybe our easiest to remember. That many volts. This is not. Why is this not a good question? Because you'll never see a 2 coulomb charge. But I did want to take the opportunity to point out that 9 times 10 to the 9 can be dealt with in your head when you deal with simple small energies.
What's like a charge, like if you told me like an object?
What would the electrical potential energy of the system be if I brought a 3 coulomb, again way too big, if I brought a 3 coulomb charge right there? Someone I haven't heard from in a while. I brought a plus 3 coulomb charge from far away to right there. What potential energy would it be? How much work would I do? Some?
5.4 times 10 to the 10.
5.4 times 10 to the 10 joules of energy. Cool. And I could do that either by using this formula directly or by multiplying that 3 coulomb charge times the voltage at that location. And that's all you're going to do. I don't want to talk about that.
Mr. Siegel,
Let's go on. We got coulomb. Yeah.
you keep saying that like 3 coulombs is like a giant thing, but
Yeah.
I have no perspective on on coulombs and like objects. So can you tell me like an object that I will be, or people will be vaguely familiar
Yeah. When I charge up the Van de Graaff generator enough that you don't want to touch it, I would say it has between a microcoulomb, or between a nanocoulomb and a microcoulomb.
Oh.
So is that a single coulomb? You'll note that I gave 3 orders of magnitude of uncertainty. What the point is way smaller than a coulomb.
Don't touch.
I forget. Why? Yeah, I forget. There's a reason, and I used to know it. Let me look that up. Why is a coulomb so big? Right.
The base unit of something like that. What is something you would normally get?
To do with
The lecture.
I think it has to do with capacitors, maybe with electrical current. Because an amp is a lot of current. But your house draws several amps. Like you have maybe a 250 amp circuit on your house, and an amp is a coulomb per second. So I think that flowing charge has to do with amps. How much work is done by the electric field when an electron travels from ground to a location where there's 6 volts? Yeah, what is the Q? What is the charge of an electron?
1.6 times 10 to the negative 14.
How do you guys get 14? Something even. I think it's like
Forward. Yeah, I guess. Sometimes this is just called E, the elementary charge, which can be positive or negative. A proton has positive E of charge, and an electron has minus E of charge. The E has a value of 1.6 times 10 to the minus 19 coulombs. So, what have I dashed hot painted here? The fact that ground is another word for a place where voltage equals 0. The ground is where voltage equals 0. So remember this, the amount of work that's done in general is the amount of charge times the difference in voltage. That's, let's see, minus 1 elementary charge times the potential at P minus the potential at infinity. And what is the potential at infinity again? 0. Very good. 6 electron volts, that's the amount of energy, that's the amount of work. Aha! Another unit. Electron volts. What is an electron volt? Well, an electron volt is the amount of work associated with 1 electron charge moving across a voltage difference of 1 volt. If this location and this other location different voltage by 1 volt, and an electron travels from one location to another, then the potential energy changes. By how much? How much work was done? 1 electron volt. 1 electron crossing a 1 volt difference.
Is that a joule too?
An electron volt is not the same as a joule. Let's see what the relationship is. 6, there's the elementary charge, right? So it's 6 of 1.6 10 to the minus 19 joules. 1 electron volt is 1.6 times 10 to the minus 19 joules. Yeah. You're welcome. Yeah, it's a tiny joule. Tiny, of course, referring to 1.6 times 10 to the minus 19. Okay. What's the electrical potential there? Did I go too fast? Did I go too fast through that last slide? Electrical potential right there. There is a walrus of 1 coulomb, and that distance is 2 meters.
Too bad,
Don't know. The formula that we have is for a point charge. I would need to tell you more information for you to do an integral. Not without more information. You might say, what's an example of something that I could solve? And I might say, a ring of charge. What's the potential there? And actually, that's a much easier question. Okay, the following slide contains the problems that physics teachers most love to ask
Your discretion
about this stuff. Tell me, what's the electric field at that location? This is key. Talk to your neighbor. Talk to your neighbor in 1 minute.
Tell me, Sam, what do you think? What's your opinion?
In terms of R and Q, tell me the electric potential at that location and the electric field at that location.
So Sam, what's the electric potential?
Go.
Is there anything you'd like to tell our listeners?
No.
Here, I'll do the director's commentary. How's it going, period 2? I'm really glad to see you. And I know you're really glad to see me too, if you've made it this far in the video. This is actually the only, the rest of the stuff that we've talked about isn't important. I've managed to destroy the class, I'm sorry.
No! That is 0.
That's all 0. It's all 0.
Full star. It's positive, negative, physics class. I push you, and then I push you.
Let's talk about electric field.
I challenge you to.
All right, guys. Someone tell me about the electric field at point P. 0. 0. How come?
Yes.
Because what?
Yes.
Yeah, that's true. That's true. How do you? What's like the first intellectual step to answering the question? What is the electric field here? You imagine a positive charge at that location. You draw an electric field diagram. A positive charge placed there would experience an electric field from that charge pointing in what direction? To the right. And an electric field from that charge pointing in that direction. Great. So you'd have 2 equal magnitude electric fields with an electric field of 0. Yes, the electric field at point P is 0. What is the voltage at point P? Why not 0?
We just plugged it into the equation.
Which equation? What?
Well, I kind of thought that was like you treat it individually from both points, and then since your test charge is in the same location, it'll be a sum of all of the potentials that are surrounding it.
Okay.
It's a triangle.
Kind of in a parallel, maybe.
Kind of like the triangle. Yeah, it's true. Because if there were a charge there, then it would have an interaction with that charge and that charge. Joseph?
Could your R in this case be negative? For saying like it moves from
Good question.
negative to positive?
No. That amount of separation is what's meant by R. So wait. What? Oh my gosh. I guess we'll have to do it ourselves. The electric field. If this is charge 1 and that's charge 2, the electric field is the electric field from charge 1 plus the electric field from charge 2. That is that electric field plus that plus that electric field, which is 0. The voltage at that location is equal to the voltage associated with charge 1 plus the voltage associated with charge 2. That's equal to K times Q over R, right? Plus K times Q over R. That's 2KQ over R, as Vanessa said. So, physics teachers just love this. Can't you imagine like the square that you're going to get with like, it's wonderful. And the electric field at the center might be 0, but it would be like 4 of the potentials associated with each charge. I'll leave the rest to your reading because we're out of time. And you have a web assign that is due the next time we meet. Which
Exactly one is very
Don't do that.
No, hopefully
Don't
do
it.
Thank you.
Me?
Video out.